Okay guys, let's get started on the third page of our lecture notes. And here we're going to be talking about the combined gas law. So here we're going to look at what happens when you've got three variables and any one of those can change or any two of those can change. All right, so this is the combined gas law, and this is P times V divided by T, the temperature in Kelvin, is equal to a constant, or the big complicated thing of P1 V1 over T1 equals P2 V2 over T2, and of course it looks like this, right? We've got a pressure and volume and temperature in one situation and the pressure, volume, and temperature in a second situation, and any one of those could change. So let's look at the example on our page there. It says a gas with a volume of 201 liters is at a temperature of 293 Kelvin with a pressure of 224 millimeters of mercury. What will the volume of the gas be at STP? So I have to be careful here because we think sometimes when it says STP that we haven't been given a change, but we actually have, because we know what the temperature and pressure will be at STP, so we can plug that in. So this is going to look like, so our first situation is that we have a volume of 201 and the the pressure is 224 millimeters of mercury, and the temperature is 293 Kelvin. And we're going to standard conditions, which puts us at 760 millimeters of mercury and a temperature of 273. And then we're going to solve for V2. Now here we've got all these numbers. We've got 6 possible variables. We've got 5 pieces of information given. So it's easy for us to solve for that unknown. We're just going to multiply, 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 divide, divide, right? So if we wrote all that out, that's what it would be. But we're going to cross multiply this way and then divide by the 2 pieces of information that are connected to our unknown. So it's 224 times 201 times 273 divided by 760 divided by 293. And when you chug that out, oh, what do we get as an answer? Did I write it down? I did not. So what do you get? I got I got 55 liters. Did it again. 55 liters. Is that what you got? We should have gotten the same answer there. Okay? All right, so let's move on to the ideal gas law. The ideal gas law considers the number of particles or moles of a gas, but the conditions are not changing. So this is PV equals nRT, or my friend PV nert, okay? So here we have to understand that gas law constant. Remember, the universal gas law constant is 8.315 liters times kilopascals over mole Kelvin, or 0.0821 liters atmosphere over mole Kelvin. And we're going to choose the constant based on what our pressure is given to us. And because temperature is always going to be in Kelvin, our volume is always going to be in liters, so it's just our pressure that will change. So if the pressure is in kilopascals, we'll use 8.315. And if the pressure is given to us in atmospheres, then we will change it. We'll use the constant 0.0821, and if the pressure were to be given to us in something else, we would convert to one of those things so that we can use that constant. Okay, so the example that we have here says the average lung capacity for a female student is 3.9 liters at normal body temperature, which is about 37 degrees Celsius, and 110 kilopascals. How many moles of air could her lungs hold? Well, this is just our PV nert application, where we have the pressure at 110 kilopascals. The volume is 3.9 liters. We want to know how many moles of air that would be. The R, which R are we going to use? We're going to use the R that has liters and kilopascals. So this time it'll be 8.315 liter kilopascals over mole Kelvin times the temperature that we've been given. And here we've got to take that 37 degrees Celsius and add 273 to it. So we're going to get 310 Kelvin. So plug all your numbers in, right? And give that a whirl. Pause if you want to hang on to what the answer is. And then I will flip my board around. You got that one done? Here we go. The answer is 0.17 moles of air in that female student's lungs when she has breathed in 3.9 liters at that temperature and that pressure. Okay, here, let's go on to Avogadro's law. Avogadro's law says that equal volumes of a gas under the same conditions have the same number of particles. And so this just means that at STP, 1 mole of a gas occupies 22.4 liters of space. Okay, so 1 mole, let's write that down. Get that into our notes. We did that last week. 1 mole, right? 1 mole of the gas equals 22.4 liters, right? And, well, there we go. Cannot write that correctly. There we go. 22.4 liters. Writing backwards is hard, guys. Okay, so let's get this one up, and we're going to come back and solve a problem with some stoichiometry, and then look at Dalton's law of partial pressures. See you in a few.